Welcome to class of physics. In previous video, I studied the elastic collision in laboratory frame of reference as well as in center of mass frame of reference. So in this video, I am going to discuss the inelastic collisions in laboratory frame of reference. So as we know, the inelastic collision is a collision in which the only momentum is conserved. It is momentum is conserved but not kinetic energy. So this condition we are using here. If kinetic energy is not conserved, that means some amount of the energy may be converted into another form. Let it be. Let's see the inelastic collision in laboratory frame of reference. Here we are considering two particles of masses m1 and m2, and they are having velocities e1 and e2 before the collision. Since the two particles stick together on impact, what happens after the collision? Those two particles are stick together. See here, there are two particles, 1 and 2. Now it has mass m1 and it has mass m2. After the collision, these two are moving, stick together. Okay, now these two have velocity v. So it has velocity u1 and it has velocity u2. Okay. Now these two are going to collide with each other. After collisions, they are moving with velocity v and they are stick together. Now, according to law of conservation of momentum, what is the law of conservation of momentum? Momentum before collision is equal to momentum after collisions. Now, before collision, we have to find the momentum of these two objects. Okay, so that is the momentum of this object is product of mass and its velocity. So it is m1 u1, and the momentum of the second object is m2 u2. Now the total momentum is, we have to add these two, then it becomes m1 u1 plus m2 u2. So after collisions, these two objects are having velocity v, and what about the mass? They are stick together and the total mass is the sum of these two masses. For that, after collision, the momentum is m1 m2 is the mass of the system into its velocity is v. For that is equal to m1 plus m2 into v. Now we have to find the velocity of the object after the collision. So that is u. We have to find this value of v. For that, I am considering a condition here, that is the second particle of mass m2 is at rest. Okay. Now I am going to impose an conditions. The second particle of mass m2 is at rest. So that is u2 is 0. Now take u2 as 0 in these equations. Then this equation becomes, so this vanishes, it becomes 0. The remaining is m1 u1 equal to m1 plus m2 into v. So this is the equation, m1 u1 equal to m1 plus m2 into v. Our aim is to find the value of v. For that, keep v one side, remaining into another side, then that equation becomes v equal to m1 u1 by m1 plus m2. So this is the velocity of the two objects which are stick together after the collision. So next, what about the kinetic energy? The kinetic energy is not conserved in case of inelastic collisions. So there may be a loss in kinetic energy. So that one we have to find the loss in kinetic energy. So that is loss of kinetic energy. Again here we are going to impose a conditions. The second object of mass m2 is at rest, that is u2 is 0. Let's see here. So kinetic energy of the particle before collision and kinetic energy of the particle after collisions. So what is kinetic energy expression? It is 1 by 2 mv square. Now before collision means, so this system, we have to find the kinetic energy of this system. So first particle having velocity u1 and mass m1. For that, the kinetic energy of this particle is 1 by 2 m1 u1 square. What about the second? So second is at rest, u2 is 0. For that, it does not have any kinetic energy. The only kinetic energy before collision is 1 by 2 m1 u1 square. Then what about after collision? So after collision, these two are stick together having the mass m1 plus m2, so that the kinetic energy becomes 1 by 2 m1 plus m2, and velocity is v, it is v square. Okay, so that means the kinetic energy conservation as 1 by 2 m1 u1 square equal to 1 by 2 m1 plus m2 v square. So that is why we are using here. The kinetic energy before collision is this one, 1 by 2 m1 u1 square, and the kinetic energy after collision is 1 by 2 m1 plus m2 v square. From these two equations, I am going to substitute the value of v. From this equation, we know already value of v after collision, the velocity. Okay, substitute v value in these equations, then simplify. Okay, I am going to substitute here 1 by 2 m1 plus m2 into v square. V square value is what? m1 u1 by m1 plus m2 square. Okay, so this can be written as 1 by 2 m1 plus m2 into m1 square u1 square divided by m1 plus m2 into m1 plus m2, because it is square. So this m1 plus m2 is get cancelled. The remaining is 1 by 2 into m1 square u1 square by m1 plus m2. So that is here. Now loss of kinetic energy means there may be a loss in kinetic energy after the collisions. So before collision it has more kinetic energy, after collision it loses some of kinetic energy, becomes less kinetic energy. So that to find loss in kinetic energy before collision minus kinetic energy after collision. So before collision kinetic energy is here. So this is the expression for kinetic energy before collision, and now the kinetic energy after collision is this one. So that 1 by 2 m1 u1 square minus 1 by 2 m1 square u1 square by m1 plus m2. From these two equations, m1 u1 square is common. Okay, take m1 u1 square common, m1 u1 square common. Okay, then here remains only 1 minus of, so in this equation the remaining is m1 is left divided by m1 plus m2. Okay, so now take m1 plus m2 LCM from this from the bracket. So then simplify, then it becomes 1 by 2 m1 u1 square m1 plus m2 minus m1 divided by m1 plus m2. Okay, so here plus m1 and minus m1 get cancelled. The remaining is 1 by 2 m1 u1 square into m2 by m1 plus m2. Okay, so that is the loss in kinetic energy. Here it is. Okay, so this is a positive sign. That positive sign always shows there is a loss of kinetic energy. Okay, so this is the case of inelastic collision in laboratory frame of reference. Its velocity after the collision as well as the amount of change of kinetic energy during the collisions. Okay, so then one more case is there for inelastic collision, that is in center of mass frame of reference. Let's see that one. So inelastic collision in center of mass frame of reference. Inelastic collision in the center of mass frame of reference. Find no external force is applied. The velocity of the center of mass for two particle system is given by PCM equal to m1 by u1 u1 plus m2 u2 by m1 plus m2. This is the standard equation already I derived in beginning classes. The velocity of center mass is what? It is m1 u1 plus m2 u2 by m1 plus m2. This is only for system of two particles. If three particles, then it is one more is adding here, m1 u1 plus m2 u2 plus m3 u3 by m1 plus m2 plus m3, like that. Only are considering two particle systems, so that this is the center of mass. Okay, and m2 is rest. In that condition, the velocity of the second particle is 0. The velocity of center of mass in laboratory frame of reference is given by v center of mass equal to m1 u1 by m1 plus m2. Here this term is vanishes because it is equal to 0. In other words, center of mass reference frame moves with respect to laboratory frame with velocity center of mass. Okay, let u1 prime and u2 prime be the initial velocities of masses m1 and m2 in center of mass frame of reference. Okay, see here, u1 and u2, so these are the velocities with respect to laboratory frame of reference, and u1 prime and u2 prime are velocities within center of mass frame of reference. Okay, so in these two frame of references, the velocity of center of mass is v center of mass. So because these two are moving with respect to one another, so now by the transformation equation, u1 prime equal to u1 minus v center of mass. Okay, so what is u1 prime? So this is the velocity of the first object in center of mass frame of reference. Okay, u1 is velocity of first object in laboratory frame of reference. That is, we are going to comparing these two frame of references. Then u1 minus of m1 u1 by m1 plus m2, because already we know velocity of center of mass, so that is here from this equation substitute the value of v center of mass, then it becomes u1 minus of m1 u1 by m1 plus m2. Now from these two terms u1 is common, take common, then it becomes 1 minus of m1 by m1 plus m2. Okay, same, simplify this again, take m1 plus m2 as LCM, then it becomes u1 into m1 plus m2 minus m1 divided by m1 plus m2. Okay, so then m1 get cancelled, the remaining is u1 into m2 by m1 plus m2, so that u1 prime is equal to m2 by m1 plus m2 into u1. So that is the velocity of the first particle before collision in center of mass frame of reference. What about the second particle? Second particle is not zero in center of mass frame of reference, but in laboratory frame of reference the velocity of second object is 0. So we have to find the velocity of the second particle before collision in center of mass frame of reference, that is u2 prime, that is equal to u2 minus of v center of mass. Okay, so u2 is 0 in laboratory frame of reference. Now take the velocity of center of mass minus of vcm, so that u2 prime is equal to minus of m1 u1 by m1 plus m2. After collision, the two particles stick together and have combined mass, hence the final velocity in center of mass frame is 0. Okay. In case of center of mass frame of reference, what happens? Center of mass is approaches to second objects. Okay, that means the center of mass is at rest, of course. Then from the center of mass, we looks like this second object only approaching the center of mass. After collision, these two particles are stick together and center of mass is here, so now they are moving. Okay, so but these two stick together to the center of mass frame of reference, that's why these two looks like at rest in center of mass, but in laboratory frame of reference these two are having the velocities, so that here we are mentioning velocity in the center of mass frame is 0. Okay, that is stuck particles are at rest in the center of mass frame of reference, but have velocity in laboratory frame, so that velocity is m1 u1 by m1 plus m2 v center of mass in laboratory frame. So this equation we derived in case of laboratory frame of reference. So these two are the inelastic collision in laboratory frame of reference as well as in center of mass frame of reference. In next video I am going to discuss the collision in variable masses. If the mass is varying, then what about the conservation of momentum? Okay, so not